This is the second in a two-part series discussing the effects on equilibrium of changes to our system using the Le Chatelier's principle. In the previous video, we talked about altering concentrations and the effects that that would have on equilibrium. In this video, we will focus on changing pressure, volume, and temperature. According to Le Chatelier's principle, any change that you make to a system that is at equilibrium, the system will move in such a way to partially undo that change. So if we change the volume, this is really only applicable for gases, right? For liquids and solids, you can't really change the volume of them. They are incompressible. So changing the volume of the gas, the system will move to counter the change. So if you reduce the volume, that would be via compression, the reaction will move to the side with less gas molecules. So what you'll do is you look at the balanced chemical equation, decide whether the reactants or products have fewer gas molecules, and then upon compression, the reaction would shift to the side that has fewer gas molecules. Conversely, if you expand by generally pulling the piston away or increasing the volume, the reaction will move in such a direction to produce more gas, thus filling the volume that you have made. Temperature changes, the system will move to counter the change. So if you increase the temperature for an exothermic reaction, that is a reaction that gives off heat. So if you increase the temperature, the way that you would do that would be by adding heat to the system. So if you add heat to a reaction that gives off heat, you can think of heat as a product, and so the reaction will shift back towards the reactants. If you decrease the temperature on an exothermic reaction, that would pull the reaction towards forming more products. We can add components. We already talked about adding reactants and products in terms of changing concentration. But we could also add other things. We can add inert compounds, such as argon gas, or we could add a catalyst. And we will be looking to see what effects these additions have on our system. For gas phase reactions, we can add multiple different types of gases. We could add one of our reactants or products. Adding either a reactant or product will increase the partial pressure of that component. It will not increase the partial pressure of the other components. So if we add one of our components, it will increase the partial pressure. This will affect the system that had previously been at equilibrium. So if we add a product, by Le Chatelier's principle, that says that the reaction will move in such a way to remove that product that we added. So if we add one of the product gases, that will increase the Q value, and if Q is bigger than K, then the reaction must shift to the left to form more reactants. We can also add an inert gas to the mixture, which will have no effect on the position of the equilibrium. By adding an additional gas component that does not participate in the reaction, it will not affect the reaction. This would be similar to an aqueous phase reaction if we dumped a different salt into the solution that did not react with any of our components. If we add a component that does not participate in the reaction, it will have no effect on the reaction. So adding an inert gas like argon to most reaction vessels will have absolutely no effect on the position of the equilibrium. That argon gas or any other inert gas does not show up in the equilibrium constant equation, and so it will not affect the numerical values that we are plugging into the equation. We can also affect an equilibrium by changing the concentration, but only for gases. The reason this works is if we decrease the volume of a container, let's say we have a container full of gas molecules, the concentration, you can think about it in terms of concentration. Our concentration of component A is equal to essentially the number of moles divided by the volume. If we decrease the volume, making it smaller, so if we move the piston down here, then the volume goes down, but the value for A will go up. So we're in essence changing the concentration value that is going into our equilibrium equations. Now, because all of the gases are in there, we are changing all of the concentrations. What the effect will have depends on the exponent of the values in our equilibrium equation. The higher the value in the exponent, the bigger the effect it's going to have. But this will only apply to gases because gases are the only ones that are compressible. The more the exponent in our equation, the more the effect. In terms of Le Chatelier's principle, we can simplify this by saying if we reduce the volume of the gas, then the reaction will move in such a way to reduce the amount of volume needed for the gas. How that will work is if we have, let's say, a reaction of 2A going to a single B, the B value, if these are both gases, if they are both gases, the B value takes up less volume. So when we decrease the volume, the reaction will move in such a way to use up less volume. So it will move to the side that has less moles of gas. So by decreasing the volume, the reaction will produce more of our product, B in this case. For things that are in solutions or solids, they are unaffected by changes in volume. Because solids and liquids are incompressible, the only thing that we can really change the volume without removing material is gases. So changing the volume will have no effect on the concentration of solution. The reason for it is the only thing that can change volume without removing substance is a gas. If the partial pressure increases, then the total pressure in the container will also increase. According to Le Chatelier's principle, the equilibrium will shift in such a way to remove that pressure, and that will move to the side that has less moles of gas. Right? So you will have more, in the case of the example we had, you'll get more B and less A. The way that the system will reduce the pressure is to reduce the number of gas molecules in the container by going to the side that has less moles on it. When the volume decreases, the equilibrium shifts to the side with fewer gas molecules. Thinking about this process of decreasing the volume, you could also think about it in terms of increasing the pressure. By decreasing the volume, because the pressure and the volume are inversely proportional, if we take our volume and push it down, we are in essence taking our pressure and moving it up. So by increasing our pressure, the system will move in such a way to reduce the pressure, and it does that by going to the side of the reaction that has less moles of gas. Now, temperature is a little bit different from concentration and volume and pressure. By adjusting the temperature that a reaction is taking place, we are actually changing the equilibrium constant. But we can still use Le Chatelier's principle to help predict the direction that the reaction will proceed. What we need to know is the process exothermic, meaning that the reaction gives off thermal energy, or endothermic, meaning that the reaction consumes thermal energy. So if a reaction is exothermic, that means that as the reaction proceeds, it will get warmer. Endothermic reactions, on the other hand, as they proceed, they will get colder. We can adjust how we're writing our balanced chemical equations to take into account whether a reaction is exothermic or endothermic to help us use Le Chatelier's principle by writing out the term heat as either a reactant or a product. So in the case of exothermic processes, we're going to write heat as a product. In the case of endothermic, we will write it as a reactant. So you take your normal reaction, let's say A plus B goes to C. If this is an exothermic reaction, then heat is a product. So to use Le Chatelier's principle, we would say plus heat. And then the way that you increase the temperature is by adding heat. So if we have an exothermic process and we're adding heat, then the reaction needs to go in such a way to reduce the heat or reduce the temperature. So it will go back towards the reactant side. The reaction will proceed back towards the reactants. And this is a reversible reaction. Let's say we have A plus B equilibrium, and this time it is endothermic. That means that heat is needed as a reactant. We have to heat the reaction to get it to proceed. So heat is a reactant. In essence, the reaction is pulling heat from the surroundings. So if we increase the temperature, so if T goes up, we are in essence adding reactant. This will force the reaction to go towards the products. So again, the effect of temperature change, we can write out the heat as a product for exothermic reactions. By increasing the temperature, it's like adding heat, and according to Le Chatelier's principle, the equilibrium will shift away from the added heat. So if we have an exothermic reaction, heat would be written as a product. If we say that we are increasing the temperature, then the reaction will try to remove the heat that we are adding. So if T goes up, the reaction will shift to the left to get rid of the heat. If, however, we cool the reaction down, if T decreases, then the reaction will shift to the right. The reaction will try to produce more heat. Conversely, if we have an endothermic reaction, for endothermic reactions, heat is a reactant. We will write heat on the reactant side. Increasing the temperature is like adding heat. So if we're increasing the temperature for this particular system, N2O4 plus heat goes to NO2, what we would see is that our colorless gas, which is the N2O4, the container would end up turning sort of a dark brown from the formation of NO2. So if we add heat to an endothermic process, the reaction is going to shift to the right. That is what we should see. If we remove heat from an endothermic process, the reaction will shift to the left to form more heat. So, applying this to our previous example of the N2O4 being a colorless gas, if we heat this up, it ends up forming this NO2. This NO2 that we see here in our vessel, and that is this part of our reaction, this is actually the component in smog that makes it dark brown. So if you look across the horizon on a warm day in the summer, you will typically see, pretty much wherever you are, a brown gas or a brown haze, particularly if you're close to cities, a brown haze on the horizon. In the winter, you'll notice that the skies will appear more blue because the reaction has been shifted to the left. In winter, we're essentially doing this equilibrium at a lower temperature, and because heat is a reactant, the reaction will move in such a way to produce more heat. So the equilibrium will lie more towards the colorless gas. So typically in winter, the skies appear to be more blue than they do in the summer. In the summer, the equilibrium shifts towards the product side and you get more of that brown haze on the horizon. The pollution is still there, it's just on cold days the N2O4 is favored and on hot days the NO2 is favored. The last thing that we could do is add a catalyst. In our previous discussions on chemical kinetics, it had been mentioned that the addition of a catalyst provides an alternate, more efficient mechanism, one that has a lower barrier of reaction. Because the barrier of reaction is a barrier in both directions, this would actually speed up both the reactant and the product. So if we take our potential energy diagram, and this is our reactant and our products, if we provide an alternate mechanism, one that has a lower barrier, it maybe is a two-step process, but both steps have a lower barrier. This reduces the height of the barrier in both directions. So the addition of a catalyst doesn't actually shift the location of the equilibrium. It will mean that you will reach equilibrium faster, but it will not affect the position of the equilibrium because it will affect both the forward and the reverse processes by the same factor. So catalysts do not affect the position of equilibrium. They will affect how fast you get to equilibrium, but they will not affect the ratio when you get there.